Hello, welcome, as it were, to this talk. This is joint work with Marcelo from my PhD, and it's about proving coherence for Cartesian closed bicategories. There's two proofs in the paper, one which has a kind of traditional style, and one which employs some version of a normalization by evaluation argument. And what I'm going to try and do in this talk is present a little bit about Cartesian closed bicategories and why you might be interested in the kind of structures they axiomatise. I'm going to try and draw out some consequences of this coherence theorem, and finally to give you some hints about how this normalization by evaluation argument can be reconstructed from the categorical one. Okay, so let's talk about Cartesian closed bicategories. So these are some examples of where they occur. This work that we're doing here was motivated by the example of generalized species, which is a model of linear logic, but it was motivated more by Marcelo's work on higher category theory. Other examples appear around operads on concurrent games, and Marcelo and I showed in a LICS paper last year that the internal language for a Cartesian closed bicategory is some version of the simply type lambda calculus in which you add in an explicit substitution operation and some extra syntactic objects called rewrites, which model the two cells. And I'm going to come back to this example later. So in the paper, we have two proofs of coherence, like I say, and the kind of slogan for them is all pasting diagrams commute. So the slogan for Maclane's coherence theorem from an order of categories is all diagrams commute, but here we're talking about diagrams of two cells, or rewrites if you prefer, so they're pasting diagrams. The two consequences that I'm going to try and talk about here, first, because there's this nice correspondence between this type theory and the simply type lambda calculus, we can extract some facts about rewriting. And second, because this is a coherence theorem, we can talk about constructions in these kind of more semantic domains, and we can show that actually they greatly simplify thanks to this coherence theorem. Okay, so let's start by talking about Cartesian closed bicategories, and I want to start off this sort of idea by motivating why bicategories appear in theoretical computer science at all. So the example that I have in mind is that a bicategory is axiomatizing what you get when you define composition using a universal property. So you might be interested in, say, spans or something like graphs or proof-relevant relations or something like this. And the natural way to define composition of these things often involves some kind of limit. In this case, it's involving a pullback. And if you compute this in set, you'll see it's really doing the thing that you want it to do. But pullbacks are limits. Limits are unique up to isomorphism, up to unique isomorphism, in fact. So this composition operation is not going to be associative on the nose, but it will be associative up to isomorphism, and these isomorphisms are going to be quite nice. Okay, so this is the kind of structure that is axiomatized by a bicategory. And just to fix the terminology, let's just sort of go through the names of things. So you have objects, just like you do for a category. You have morphisms or one cells between your objects, and you have two cells which are now morphisms of morphisms. So you could think of your objects as categories, your morphisms as functors, and your two cells as natural transformations, and you'd get this kind of structure. Actually, if you ask for the composition operation to be associative and unital, what you get is called a two category, such as the two category of categories, functors, and natural transformations. But what we're interested in here is something a little bit weaker. So we ask for isomorphisms which witness the associativity and two unit laws of composition, and then we ask for these isomorphisms to in turn satisfy some axioms. And in fact, if you instantiate this with a single object, you get exactly a monoidal category, with these three isomorphisms being the associator and two uniters of a monoidal category. So a bicategory stands in the same relation to monoidal categories as a category stands in relation to monoids. Bicategories turn up actually in quite a few places, and I've just given some examples here to highlight them. These aren't all Cartesian closed, and I'm not going to say much about them, just to highlight the idea that bicategories collect together data in ways that actually turns up in the wild, as it were. In this talk, of course, we're interested in Cartesian closed bicategories. So what does it mean to be Cartesian closed? Well, for a category, you equip it with some isomorphisms which witness the products and exponentials. In this case, what we can do is we can equip it with equivalences. The reason is these, instead of being Hom sets, these now consist of morphisms and two cells between them. So these are Hom categories. So the isomorphisms can be stated instead as equivalences of categories. And if you think of an equivalence as an isomorphism up to isomorphism, you can now think of a Cartesian closed bicategory as a CCC up to isomorphism in a very rough sense. And I'll bring out this kind of intuition a little bit more as we go through. So it's quite useful to spell out these equivalences in a little bit more detail. We don't just ask for equivalences, we ask for adjoint equivalences, which has some nice effects. So if I just ask for an isomorphism here, the two equations I get to make this into an isomorphism correspond to the beta and eta laws. On the other hand, an adjunction or an adjoint equivalence is an adjunction in which the unit and co-unit are invertible. So what happens, instead of having beta eta equations, I now have beta eta isomorphisms, which are witnessed by the co-unit in this case and the unit in this case, and likewise for exponentials. And now, because these adjunctions need to satisfy the triangle equalities, we need the unit and co-unit to be related somehow, what you mean is you get equations that look like this. And I think these equations say something kind of sensible when you think about them in terms of rewrites for something like the simply type lambda calculus. So what this says is, well, I've got some projection here, I'm going to eta expand it, and then I'm going to beta reduce it again, and I get back to the same term. So I might as well have done nothing at all. And this is the kind of thing that the equational theory says. So the way I think about a Cartesian closed bicategory is you take a CCC, you replace the beta eta equalities with beta eta isomorphisms, and you add in some equations that say broadly sensible things. Okay, so now we have a better idea of what it means to be a Cartesian closed bicategory. Let's talk a little bit about coherence. And I think it's something not often made obvious, but coherence is often stated in different ways. So if you look at Maclean's original paper, or his kind of slogan, all diagrams commute for monoidal categories, he's isolated some class of diagrams and he's shown that everything in this class is going to commute. And his proof is quite syntactic. It's by induction on the structure of the diagrams using the axioms. On the other hand, you might want something that's a little bit more semantic. And here you could say, for example, every weak thing is equivalent to a strict thing. So every bicategory is equivalent to a two category, or in the one object case, every monoidal category is equivalent to a strict monoidal category. Now these two statements are generally equivalent. I don't know any examples in which they're not, but there is a little bit of argument to go between them. And we give one of these arguments in the paper. Actually, we give two proofs in the paper, as I've said, one of which is this kind of two categorical universal algebra style, which was developed by the Australian school in the 80s and has some extremely powerful machinery attached to it. But the second of which is a kind of middle way. And I think this is a middle way because it involves some kind of syntax, because we're using internal language, but it's also kind of semantic because we're using a semantic argument to prove normalization of this language. So I think of this as a kind of denotational semantics approach to coherence. So these are the two that are in the paper. But the one that I want to talk about here is this one. And the reason I want to highlight this is because I think it has some nice kind of properties. So I'm certainly not a rewriting theorist or a proof theorist. I'm not in the bicategory theory enough to really find these kind of proofs extremely intuitive, but I do feel like I understand things like beta eta rewriting, long beta eta normal forms, properties, categorical constructions such as gluing or logical relations. And here we're going to use that kind of technology upgraded to the bicategorical setting for this argument. And the other thing is, once this is set up, there is a fair amount of setup involved because we have to reconstruct everything bicategorically, but it's not too much more difficult than the categorical argument. I'm going to try and hint towards that towards the end of this talk. Okay, so this is the coherence statement, and it says between any two morphisms in the free Cartesian closed bicategory, there's at most one 2-cell. So more intuitively it says, okay, so take any diagram of 2 cells which is built just using the axioms of a Cartesian closed bicategory, then this diagram will commute. And here we're going to talk about 2 consequences of this. Let's take them in turn. So let's start with this first one about beta-eta rewriting. So to understand this, I have to go back a little bit and talk about the internal language for Cartesian closed bicategories. How does this look? Well, it's a kind of type theory, so we have terms, but following the kind of traditions set by Hilkin and Hirschowitz, we also have rewrites between the terms, which model the 2 cells. And I'm not going to talk very much about this, but I will highlight some features. The first of which is that you have to include an explicit substitution operation because we want to model bicategorical structure, so we can't use substitution, which would be associative and unital on the nose. Second is that the simply type lambda calculus embeds into this type theory as a kind of explicit substitution free fragment. I kind of think of it very roughly as a sort of pure fragment of the type theory. And finally, the syntactic model has a suitable free property. So this says that I can soundly interpret every term as a morphism and every rewrite as a 2-cell in any Cartesian closed bicategory once I've chosen interpretation of base types and so on. But the reason I want to bring up this type theory is because I think of it as a logic of program transformations. And the reason is because as I was trying to draw out before when I was defining Cartesian closed bicategories, beta-eta rewriting, every beta-eta rewrite corresponds to a rewrite in the type theory. And so what this is really doing is it's tracking how terms reduce according to the beta-eta laws. So what does coherence say in this setting? Well, because this is an internal language, coherence says there's at most one rewrite between any pair of terms of the same type in the same context. And then in this is how we get our first consequence, because we instantiate this in this setting and we say, well, suppose I have 2 ways of beta-eta rewriting t to t prime. They correspond to 2 rewrites across here. Well, modulo the equational theory given by a Cartesian closed bicategory, these 2 must be equal. Okay, so now let's look at our second consequence, which is about constructions in Cartesian closed bicategories. And for this, I'm going to introduce some examples. I'm going to work with a specific example, and we're going to start with the notion of a monoid. So a monoid in a category with finite products, you take some object, you take some multiplication map, you take some unit map, and you ask for it to satisfy some axioms. If you instantiate this in set, you get exactly a monoidal category. If you instantiate this in set, you get exactly a monoid, sorry. You instantiate this in cat, you get exactly a strict monoidal category. But sometimes we're more interested in monoidal categories more generally, and so this is captured by the example of a pseudomonoid, or the definition of a pseudomonoid. What we do to define a pseudomonoid is we take the same underlying data, and then we add in extra data, which instead of saying these equations hold on the nose, we say they hold up to isomorphism. And as we have done all the way through this talk, we don't want any kind of 2 cells here, and so we ask them to satisfy triangle and pentagon laws. And indeed, if you instantiate this definition in cat, it is exactly a monoidal category. But you can do it in any bicategory with finite products. And the annoying thing with this kind of construction is it's something very natural, but often you construct these 2 cells using the universal property of a product, and so proving anything about them becomes really painful because, say, alpha is a composite of 2 cells defined using universal properties, then reasoning about them means you have to unfold them and so on just to reason about them. And so not only do you have to construct this data, you have to work with it, which quickly becomes very tedious. An example where that becomes a sort of an issue is this one. So in a Cartesian closed category, it's easy to see every endo-exponential is a monoid. You just have some identity and some composition, and you can prove this in the simply type lambda calculus pretty easily. And then you'd say, well, in a Cartesian closed bicategory, surely every endo-exponential becomes a pseudomonoid in essentially the same way. And again, the difficulty here is checking these axioms, and this is a really tedious exercise to do, something that you feel like you already know and must be true, but you're having to do pages and pages and pages of work to prove. Well, in the light of the coherence theorem, this kind of difficulty goes away because you prove this result in the simply type lambda calculus. You then prove the axioms which are using the beta-eta laws, but all of those beta-eta laws correspond to some structural 2 cells in the Cartesian closed bicategory via this correspondence with the type theory that we discussed earlier. And then we need to check these extra axioms, but these are guaranteed by the coherence theorem. So our second consequence is that calculating in a Cartesian closed bicategory for these kind of structures becomes drastically more simple. And if you've ever had to work with a higher categorical structure, you'll know that coherence theorems are really a godsend for these kind of things. Okay, so I just want to spend the rest of the talk sketching how the normalization by evaluation argument works as a generalization of the argument for the simply typed lambda calculus. So this is the kind of high-level view of normalization by evaluation for the simply typed lambda calculus. This slogan is one that I learned from Sam Linley, that you're looking for canonical representatives within beta-eta equivalence classes. So how do you do this? So I've got a bunch of terms here which are beta-eta equivalent. I interpret them semantically and then they all become equal. And then what I need to define is some quote operation which then lands only in the normal terms, in this case the long beta-eta ones. What that means is then this normal form map is just this composite across here because it always ends up in the normal forms. And the way you do this is we're going to define neutral terms, which for reasons later on it's going to be important that they include the variables. And then we're going to define quote and unquote by mutual induction. And then we can set up this triangle here that we're looking for. So Marcelo proved, he did a normalization by evaluation argument for the simply typed lambda calculus in 2002. And this is the argument that we build off for Cartesian closed bicategories. So I'm just going to talk a little bit about how this proof works, and then I'm going to point to the ways that you can generalize it to make it a bicategorical argument. So first we need to talk about syntax. And syntax we're going to treat as index presheaves. So con has objects contexts and morphisms context renamings, and newt a for any type, for some type A, takes in a context and gives you back all the neutral terms of that type in that context. And similarly, norms A gives you back all the normal terms of that type in that context. So we have some way of talking about syntax, but we also want some way of talking about semantics. And what we're going to do is glue these together. And the word glue here is significant for people that are familiar with art in gluing and similar constructions. So we take some semantic interpretation, and then we observe that the semantic interpretation gives you natural transformations. So if I start off with a term in newts A, then its semantic interpretation will land me over here, and this is going to be natural. So our strategy now has sort of 3 steps. What we're going to do is we're going to define a gluing category in which these sort of things appear as objects. So we're thinking of them as syntax and semantics paired together, glued together. We're going to pick a suitable interpretation, and then we're going to define quote and unquote as maps in the gluing category. So let's just sort of take this in stages. Let's start off with the gluing category. And I'm going to give this in detail, mainly so that then later on, those of you who are sort of more aware of the bicategorical aspects can have a sense of how the gluing bicategory might be defined. So what we're going to do is, before we had some syntax, some semantic interpretation, and then some semantic interpretation in this kind of Hom set. And we're just going to axiomatize all those bits. So instead of a particular presheaf, we're going to take any functor from the category of context into set. Instead of the semantic interpretation of some type, we're going to take any object, and then we're going to take any natural transformation between them. What does a morphism then look like? Well, it's a map from P to P prime and a map from X to X prime that behaves well with the natural transformations. So it's a commuting square that looks like this. And here, just to emphasize, what we are thinking of is we think this is syntax, this is some kind of interpretation, and this is some place where the semantics lives. And importantly, not only is this a CCC, but newts and norms with their semantic interpretation live as objects in this gluing category. Okay, so now we have this thing, and we need to pick an interpretation and define quote and unquote. And I'm just going to give you the end result of doing this. I'm going to say that quote and unquote are defined using the universal properties of Cartesian closed structure. So when you do it bicategorically, you can do broadly the same argument. So what does the interpretation look like? Well, the interpretation of some type A is going to look like some functor at the top, some natural transformation here, and some choice of object here, which is going to be the semantic interpretation of A in our original category, because of the way this gluing, this CCC structure is constructed. What is a morphism going to look like? It's going to be a commuting square that looks like this. And then what the quote and unquote look like as morphisms in this gluing category, they also look like commuting squares, look like this. But actually they look like commuting squares in which this bottom arrow is just the identity. And what that means is, if you instantiate this for the syntactic model, is that this says that quote and unquote preserve beta eta. So now I said that the way you get your normalization function is going through newts and then the semantics, or using quote and then the semantics. So what we're going to do is we're going to glue all of these together so that we end up in normal forms. And if you paste all these diagrams together, you get something that looks like this. And then instantiate it at some gamma, which is the context we're interested in. And we define the normalization of some term, which is this term here, to be this composite across the top. And this is where it's important that the variables live here. So now this takes in, the point is that this, instantiating this at these variables lands in some normal form, which is then the normal form of T. And we actually get some extra guarantees from this. So let's see what happens as we chase this diagram. So this set of variables, or this sequence of variables, going around this way becomes the identity, going across here becomes the interpretation of T, but going across here becomes the normal form. So what this says is that the interpretation of the normal form is equal to the interpretation of T in every model, because C and S here were chosen, were completely arbitrary. So in particular in the syntactic model, the normal form of T is beta eta equal to T. So now what happens when you do this bicategorically? Well, in the kind of usual style of things, all of these equalities just become isomorphisms. So you can play the whole game again. You define a gluing bicategory, you pick an interpretation, you define unquote and quote, and what you get, instead of this picture, is you get a picture in which I've put isomorphism symbols in it, and now instead of having newts and norms, I have the embedding of newts and norms inside the internal language of Cartesian closed bicategories. So once again, this norm map is the one across the top, and instead of, by playing the same game as we did before, what we can see, instead of having an equality here, is we now have an isomorphism. So what this tells us is that for every t and t prime, I have some isomorphism which only depends on t, or only depends on t prime, between its interpretation and the interpretation of its normal form. And the way you set up so now we want to use this to prove coherence. So the way we've set up the gluing bicategory is so that the interpretation of a rewrite from t to t prime forms a commuting square that looks like this. So this is the interpretation of tau in our original Cartesian closed bicategory, and this is some other thing which is given by the Cartesian closed structure of the gluing bicategory. But actually, a little bit of reasoning shows that this is actually the identity, and so the interpretation of tau is equal to this composite which only depends on t and t prime. In particular, in the syntactic model, tau is equal to some composite which only depends on t and t prime, and so if I have both tau and sigma down here, I'm just going to have to deduce that they're both equal to this composite, and so they're equal. So what this tells us is that if tau exists, it's unique. So this is how we get the statement of coherence, because if I have any rewrite between these two, it must be the unique choice. Okay, so let's summarize what we've seen so far. So Cartesian closed bicategories are coherent. This is the kind of headline. One of the consequences is that it suffices to work in a CCC in some appropriate sense. And we prove coherence in two ways, but the one I've talked about here is via this normalization by evaluation property or argument, in which coherence is seen as a normalization property for an internal language. We prove this normalization property semantically, and because the original argument for Cartesian for simply type lambda calculus works quite with universal properties, we can reuse all those universal properties to build a bicategorical proof, which really builds on the categorical one. And then obviously there's some ideas for future work there. Thank you.